Yes, fine. Right. So that problem was like with the logic error which we have written the code, but now that's okay. We will see this. So again, we have created a module full adder. Of course, as I said, port mapping can take place via two mechanism. I don't know how many of you followed that, but still, if someone has any doubt, maybe I could clarify that, because that's more important. If you make a problem with port mapping, then the whole signal assignment changes and you will get a wrong result. So I said two important things while discussing yesterday's class. One, instantiation of module inside a module. So probably like we have discussed something like this. Can you see my screen?
Yes.
Yes, sir.
Okay. Yeah. So module, n module. Inside this, say I can have one more module separately here. Module, say full ladder, so and so, n module. I can instantiate this n number of time. See, whatever name which I have given, including capital small letter, that need to be followed. So full ladder f1 times port list, then full adder f2 times port list. Like this, you can call any number of time. But remember, I am just calling the name of this module inside my module definition. You cannot go and define this module inside this module. That's what I said. You cannot define a module inside this module, but you can call a module inside another module. That you can always do it. All right. That's what we have done. Just for a minute. Right. So what happens? You why do you get like this? Right. So you can call n number of time. That's what we said. While calling, say I'm calling like full adder f1. This fourth order, say sum carry a comma b comma c. Remember, in the definition, this is module n module, and again one module outside you have discussed. Inside this, you have discussed the port list. This order should be same as this order. So whatever um, no name you have given, like some carry, it could be any name. Some su, ca, a1, b1, and c in. But the point is, the order of the signal which you have given in this full adder definition should be followed in this. If you are not following the order, a wrong signal would be assigned to a wrong value which is being computed here. So you need to make sure this is called module instantiation by order. Otherwise, by name you can do it. So same, let me try to do it. FF ladder. I'm just giving F1, one instance name, dot dot s is being assigned with su. This is what I am saying, comma, dot c is being assigned with ca, dot a is being assigned with a, comma, dot b is being assigned with b, like this, right? It keeps on. This is assigning by name, other one is assigning by order, right? That's all. So that's what we have seen here. Look at the code. We have written full adder, and we have defined input a b c n as a reg, right? We follow some c out a comma b comma cn. Output is reg. We need to declare this as a reg because the sum on the output is supposed to be taken as an output, so you need to store it. With these two has been stored as, I mean, declared as reg. And the simple always statement, whenever uh, any of these three input changes, then definitely this will enter into this loop. One important point you need to note here: inside the sensitivity list, if you use R, this R is different from the primitive R. Why? Because the same R, when it is being used as a primitive, like in the data, not data, structural modeling, that refers to gate. Whereas if I keep it inside the primitive list, I mean sensitivity list, this R refers to where literature R, that is A, RB, RC. Any of this changes, then it will enter into this block. So begin some A XOR B XOR C in, and C out, it is one AND operation, one XOR operation, and that with one AND operation. So these two signal are being ANDed up, and then finally it enters with the C in. So this will be the final. So first you can check the full adder. I have already checked it, but anyway, you can go again and use this full adder. And I'm going to instantiate this with ripple carry adder multiple times for a four times in order to get 4-bit ripple carry adder. So RCA ripple carry adder 4-bit dot b. So again, I have defined one module. So you look at the order by which I define sum C out A comma B comma C in. Now my sum is going to be of 3-bit, sorry 4-bit, 3 down to 0. C out input I have defined A and B as 4-bit, C in as 4-bit. Now look at here, the internal connections, as we discussed yesterday, carry from the first stage will be moving on to the second stage. Those things are internal to the ripple carry adder, so that need to be declared as wire. So that need to be declared as wire. That's what we have done here. Wire C0, C1, C2. Now I am instantiating the full adder module by its name. So these are my instance name. I follow the same sequence. Look at here in the code which we have already written for a full adder. So first is the sum followed by carry A, B, and C. So you could see how it happens. For the first adder, you will get S0 as your sum. Second adder, you will get S1, S2, S3. Similarly, for the first full adder, you will get the carry C0. That again will be given as an input for the next stage. So this C0 will be an input over here. And for the second stage, C1 is my carry. That will be the input for the next stage. Third stage, C2 will be the carry. That will be the input for the next stage. And this is my final carry out. And as far as AB is concerned, you can give the first one as A0, A1, A2, A3. Similarly, B1, B2, B3. All the other things remain same. The first carry is Cn. That's all. This alone you need to cross check. If you make any mistake in this, then you may not get the proper result. That's all. I have entered the module. So let's try to run now. Again, already it has been compiled. Now let me straight away go to simulation, start simulation. The module name is RCA4B. Go to work. RCA, ripple carry adder, 4-bit. Yes, I'm selecting this. I'm giving this as a selection. Yeah, you get those signals. I think I have opened multiple sites, so probably you can close whichever you don't want. One, someone carry A, B, C in. These are my intermediate wires. I need not look into it. If you want to trace and see whether you are getting somewhere, if you are getting a wrong answer, you would like to cross check, then you can do it. Select signal, go here, apply to the waveform. Now you can unlock this from the desk and yeah. So now I am feeding value for A, B, and C in. Right click and force a value. For A, you can give like 1010, and B, let me give 0010, and let me give carry equal to some 1 initial carry. Now let's try to simulate this. Yes. So this is 1010 is 10, 10 plus 2, 12, 12 plus 1, 13. So this is 1101. Now remember, wherever you keep the marker, then alone this value get highlighted. Otherwise it won't. Right? So let me change the value of A to some other value. 0111. Let me keep it. This is 7. So 7 plus 2, 9, 9 plus 1, 10. I need to get 10. Let's try to simulate again. Yeah, we get 10. So this is a simple ripple carry adder. Of course, you can extend this for any. So now we have seen how to create one module, how to call one module inside another module. This is called module instantiation. But remember, you shouldn't define one module inside another module. That is not permitted. If you try, maybe you can try and see, it will say error stating that definition of a module inside a module is not being permitted. That you will get a error code. Yes. So that's all. So almost like now one more, we will take some encoder type of circuit, and of course you can do like if you go through any standard digital book like Morris Mano and things like that, you could see almost for every digital circuit. I think now it is being associated with code also. You can try one by one. I'm just trying to show you what is what. That's all. Right, now let's take one encoder. You know what is an encoder, like, right? So what is an encoder? Can someone? What do you mean by an encoder? Because most of the places you use encoder, decoder, mux, demux, they are the basic building block for any digital system building. What is an encoder? Encoder is N to M line. Say something like this. Some 8 to 3. You can have an enable line. Right? So suppose if I am giving 0, 0, 1, 0, 0, this is an 8-bit, right? So 3, 6, 7, 8. So appropriately, that particular line will get enabled. So this is I0, I1, I2, like I7. So whichever line you get 1, that corresponding line will get encoded. So this is I2, 0, 1, 2. So you will get, let me keep the encoded value like A0, A1, A2. So these are the 3 lines. So you will get 0, 1, 0. Suppose if I am having the 7th line to be having 1 enabled, right? So this line will get encoded as 1, 1, 1. It's mere encoding. Encoding means you are compressing 8 line to 3 lines, right? So this is a bit important circuit with respect to memory. You will have a memory encoder decoder circuit at many places, right? You can also do the reverse process also, right? Okay, let's try to see how this could be done. Again, writing a code for this. You can follow any style, but you can also use equation as seen in model sim, even Maurice Mano, and you can also follow behavioral style. Any as of now, you are free to go with anything, because now we know 3 styles of coding. So now look at here, module encoded behavioral module. So D is my digital line, which goes from D0 to D7, and this is my output Y0, Y1, Y2. In fact, you can have one more enable line. You can have enable, means the chip will get enable only if enable line is 1, else you can make the complete output of a chip to be at high impedance. What is the need for that? Sometimes if you want to isolate an IC, you can do this. Of course, this has not included that enable line. You can also include one more signal enable, right? So input 0 down to 7. So 0 is my now MSB now. Now remember the order in which you give here, no, that makes a difference. 7 down to 0 means 7 will be your MSB bit, 0 will be your LSB bit. If I'm giving like this will be your MSB bit, this will be your LSB bit, like that, right? And output is 3, Y0, Y1, Y2, and the output has been declared as a reg. In fact, you can keep your reg here itself. You need not put a separate line. Now, always set D. Whenever the value of D changes, you are supposed to enter into this. Enter here, use a case statement. So 8-bit line is, say, you have made here like something like this. If the first bit is 0, so what does that mean? That is 0, 0, 0. It gives me 0. First line is 1. I mean, second D1 is 1. Then the encoded value is 0, 0, 1. Like this. You could see you can define up to all possible combination of your D. So if it comes to 1, 1, 1, then it means that all the 3 are 1. That is D7 is it encoded value is 1, 1, 1. That's all. You have entered the case and N module. In fact, you can simulate and check it out. Go here. Already it has been compiled. So encoder behavioral. Go to start simulation. Go here. And let's go with what is the module name? Encoder behavior. So simulate start encoder behavioral. Okay. So select this. So you can see the transcript window. If something goes wrong, then it will give an error here, loading error, things like this. So I'm supposed to give my input D and all others are my output. You can select that, go to waveform, and give the selected signal. Right. Now let me feed in my input force here. Uh, Let me give something like 0, 0, 1. So 3-bit over 4, 5, 6, 7, 8. Now 0, 1, 2.
I too. 010.
Yes. Um, 0, 1, 0 should be my answer. Let's try to see whether you are getting like that. Yes, 0, 1, 0 is our encoded output. So you can keep on varying some other value to check. So it's a very simple circuit. If you synthesize that, then it becomes a encoder circuit. Similarly, the reverse will be your decoder circuit, all are one. So you can write a code for gray code converter, all code converters, right? Encoders, decoders. Just the reverse of this will be the decoder. You can We have done for mux. Again, reverse of that will be the demux. In fact, all the standard textbook holds the code for that with appropriate explanation. That's the idea behind it. Okay. Now, next we will go with. So we have seen something on that. Now, one more combinational circuit. Yeah, we will see something like serial in, serial out, parallel in, parallel out. These are some of the shift register. These are again some of the basic building block which are used for making a system building. So many places you could see you would have been using a shift operator to shift a value from one point to the other point. Let's see that also. Already included. Serial in, serial out, serial in, parallel out. You can have all possible combination. Serial in, parallel out, uh, parallel in, parallel out, all four. In fact, in digital book you could see an universal shift register also that could also be coded. So this is serial in, parallel out. Let's try to see whether this is working. Serial in, parallel. I believe you know what is the serial in, parallel out, serial in, serial out. These are basically a shift registers which are playing an important role with respect to shifting a data from one end to the other end. And so say this is my 4-bit, right? So serial in, serial out moves 1 bit again and again. If you give the feedback, then it keeps on circulating. Parallel in, parallel out, you feed in a value, 4-bit value at a time, and you can take it the next clock cycle for 4-bit value as an output. So this is parallel in, parallel out. Parallel in, serial out, you load all the 4-bit at a time, and for every clock cycle you can shift one bit outside to get your value. So parallel in, serial out, parallel in, parallel out, serial in, serial out. Serial in, serial out is like for every clock cycle you push this data, push this data, push this data, push this data, and move it out. Serial in, parallel out, of course, after filling up all this, you can within a single clock cycle you can put this in one register outside. So based upon your need, you can always shift a data, rotate a data, move a data, 1 bit, 2 bit, any number of bit. So this is more important in another way also. Sometime if you are going through DSP processor design, there a DSP processor or a DSP operation require a huge amount of multiplication operation. So in order to do the multiplication operation, you require more amount of clock cycle as well as more amount of resources. To get rid of this, what people do, of course, it is one such technique. One multiplication operation can be equated to shift and add technique, or you can replace a multiplication by a shifting technique, right? This is like 2 raised to the power of n. So for every shift, you can move it through. If you want to multiply, you need to shift it towards your right. If you want to divide, you can shift it towards your left. So this is what a barrel shifter do. So you could see in your books, um, having a barrel shifter. This is also used in multiple places for the system design. Right. Coming again. Now let's see, like this is serial in parallel out. Go here, simulate, start simulation. Again, let's see what is there in the code. Yeah. So this is simple module definition. D, Q, of course, all has all these are sequential networks. So wherever I have a clock, no, in association with the clock, some activities is going to take place. Then it's with respect to a sequential network. So I have, because this shifting of operation takes place by moving a data from one register to other register. So basically, it is nothing but a D flip flop, right? So first we need to see the D flip flop. Anyway, we will look into this and then see what is a D flip flop. In fact, you have many variant of D flip flop. We will also see that. Right. So module, serial in, parallel out. D is the data, Q is the output, clock, reset. So input D, clock, reset, output is 3 down to 0, Q. So it's a 4-bit output. So what are we trying to do is, like, output is being taken with the register 3 down to 0, T, right? It's a temporary setup which has been made here. Always at passage of the clock, which means whenever the clock moves from 0 to 1, it is entering into the loop. If reset equal to 1, it is making the temporary variable t equal to completely 0. Or t is assigned with, this is a non-blocking assignment, so it can parallelly take, right? So if this is 0, t will become 0 here. Else, t is being assigned with the new data in the last LSB in addition to the previous value which you have. That is, whenever you give a new value to D, that will get added up to the LSB. That's what you could see here. And this is a concatenation operation. Can you see here? Flower brace. So flower brace is used for concatenation operation. What do you mean by concatenation operation? I believe you have noted in, say like this. I am having 0, 1, 1 and comma 0, 1. If I put them in the curly braces, you will get the output as 0, 1, 1, 0, 1. So what does it mean is, it will simply append the n bit with another m or n number of bit while you give a concatenation operation. So that's what we are stitching up here. T 2 down to 0, so it's a 3 bit. The last bit alone is being kept with the D. Again, I'm using one assign statement to assign this temporary value to the Q, because Q only we have defined that as a register output. So this register, whatever we have declared, it is an intermediate signal which has been kept for storing a value. That has been declared as a reg for the reason it is supposed to hold the value till it is getting transferred to Q. That's all. So go here, start simulation, C4, serial in, parallel out. So let's select all the signal which I need. T is a temporary signal. I don't want that. So take it to the waveform output. So now you can assign clock with clock. So make sure that all the clock signal, you need not force any value to the signal. For clock, you have a separate one called as clock. So this will have an offset of 0, duty cycle 50. So which means you will have a total period of 100 T. So 50 will be for on period, 50 will be for off period. High value will be 1, low value will be 0. And this will be a rising edge, which means whenever the rising edge of the clock need to be, you are giving the rising edge of the clock. This is the definition of this clock now. So the period is 100 nanosecond, picosecond, and duty cycle is 50%, and low value is 0, high value is 1, and the edge is pass edge of the clock. So I am just simply giving OK. I am satisfied with that clock. Right. So now let me give force D value with some 1. Let me do that. And reset, let me give first, let me give 1 and make it as 0. That's what we plan to. Yeah, now you have made it as 0. Now you make the reset as again uh, 0, because initially I want to exercise this reset so as to ensure 0. It's always important that in a flip-flop, you don't know what is the next state until unless you bring them to the known state. Because in a flip-flop or a connection of flip-flop, the next state depends upon the present state and the input again. If you are not aware of what is the previous state, then you can't determine the next state, right? So it's always better to make particularly counters or any sort of sequential network to the known state by making reset to be 0 and then go ahead for doing it. Okay, now let's, yeah, you made a reset equal to 0. Now you have given 1. Now let me give 0. Force, sorry, you can force the value 0. It will get reflected in the next clock cycle only. But let's see. You run it. Sorry. Yeah. So whatever value which I have given earlier, that was available for the next clock cycle also. And if I run one more, the value which I have given 0 will enter in. See, look at here. Even now, if I am changing the value, that will get reflected in the next clock cycle, not in the coming clock cycle. So again, let me make it as 1, and you start running it. Now again you will get 0. 1 1 0 0 you will be getting. After another one more clock cycle, this clock cycle you will get 1. See here, 0 0 1. Are you following me? Like serially I am feeding in input, and I could parallelly get the output. Like the output get reflected after one clock cycle delay. So in fact, you can change if you want. You can go ahead and change that also. Like you can keep on writing the program according to your need. Right. So this is serial in, parallel out. In fact, you could also see parallel in, parallel out. Like this, you have all possible options for it. Right. Now, before going further, moving on, let's try to see the flip-flop first, because this is more important. Defining a flip-flop. Or I just want to pick up. I don't know why it is. Yes, flip flop. First, let's quickly see what is the difference between flip flop and latch. Of course, most people might be knowing, but very quickly I will refresh. A flip flop is edge triggered, whereas latch is level triggered. What I mean to say is, say this is your flip flop, this is your D input, and this is your Q output, and of course you can have clock, right? So whenever my clock moves from 0 to 1 during exactly at this instant, whatever there in D will be passed on to the Q. How do I model this? Always at passage of
Passage.
passage of clock, then if you are satisfied only with the clock, then passage of the clock, what do you need to do? Begin. Q is assigned with the D. That's all. This is a simple thing, right? Remember, after this, it will retain whatever that has been captured at that moment till next clock cycle. Or this value get changed in Q only for the next clock cycle. It will again look at D. If anything is new, it will get sample. Else, it retain the same value. Even if the D doesn't changes, that value gets sampled and it will be given as my output. The point here is, as far as D flip flop is concerned, it is sensitive only with this fraction of time interval. The same thing when it come to latch, right? It is not edge sensitive, it is level sensitive. Means if I have, this is Q, again this is D, this is again you can take clock. Some people define, if a clock is there, then it is flip flop. If a clock is not there, they call it as latch. No, that's not the right definition, because a clock is nothing but a signal, actually a signal, right? Which toggles. And for this sake, it need not even be a symmetric clock. Any rising pulse from 0 to 1. And as far as this signal is concerned, what I need is, it could be a constant 1 or constant 0, no issue. Or even it could be a value, continuous 1, continuous 0, no matter. Because my latch is going to be sensitive towards the level. By that, what do I mean is, if it is a positive latch, during the on period of my clock, the clock here act as a signal. That's all.
నరేంద్ర గారు బండి కొంటే బాగుండు కానీ
During this whole on period, it is transparent. What do I mean by this transparent? Whatever appearing in this D, that will get reflected in Q, right? And during the off period, once you move from on to off, the last value of D will be retained for the whole off period. And again, if the clock goes to on, again during the on period, whatever there in D will get transferred to Q. So it is not the passage it is clock equal to 1. Always at clock, if clock equal to 1, right, then you need to apply D equal to Q. Or it could be a control signal even. That's why I said it may not be a clock. It can be any control signal. So the main difference is the latch opening window period is high compared to that of flip-flop. Remember, all synchronization takes place only with this flip-flop. The reason is then alone syncing all those datas at proper rise edge or fall edge. You can go with rise edge or fall edge, that's left to you. So while you make a design, so many places they make sure that the design gets synthesized to only flip flop, not latch. Both are of course storage element, but when you want to synchronize them, you need to have that as a flip flop, not a latch. That's the main reason. Next, coming to latch, coming to flip flop. This flip flop you can have synchronous flip flop, asynchronous flip flop. Then again in synchronous, you can have active reset, inactive reset, reset. Similarly, coming to asynchronous also, you can have active and inactive. When you come to asynchronous, you can have active reset and inactive reset. That's all. So here you can have 4 options. 2 for synchronous and again 2 for synchronous. That's all. Now let's try to see what is this. What do you mean by synchronous, asynchronous? The other things are mere simple idea. What do you mean by synchronous?
Clock depends on
Yeah.
synchronous means clock dependent. Asynchronous means this is not dependent on clock.
Only that alone? Can anybody else? One more. Sorry, I just forgot to. Synchronous reset. Synchronous, asynchronous reset. Actually, it should be like this. Flip flop with synchronous reset, asynchronous reset. Now, can someone tell me?
Synchronous and asynchronous.
Yeah, synchronous reset. Flip flop, D flip flop with synchronous reset, D flip flop with asynchronous reset.
Synchronous, which happens at the same time. Asynchronous, events or thing will happen at different time or speed.
Okay, so can you define how the code will be?
In synchronous, always passage, always at the rate passage only. In asynchronous, always at the rate passage or passage reset also.
Okay, good. The point is very simple. Now look at here. Let me make it as clear now. Always at pass edge of the clock. This is for, I am saying, synchronous reset. This is always at pass edge. Of course, you can have one more variety also, neg edge also. You can have it. Okay. Pass edge of the clock, comma, pass edge of the reset. Reset. Now, what do I mean here is synchronous reset. Say your system is working. Let's have your D flip flop, D to Q. Now, this is my clock. This is my reset. If you give reset equal to 1, then the output will not go immediately to 0. This will come into effect only during the next clock cycle, passage of the next clock cycle. That's what this says. Though you make reset as 1, that is in sync with the clock, whenever clock reset take place, then alone it will happen. You can also have this as a negate also, as I said. Now time being, I am considering only the passage. Always at passage of the clock, if reset, if I don't mention anything, it means that reset equal to 1, q equal to 1 tick binary 0, else q equal to d, begin and end. Whereas here what happens, asynchronous, irrespective of whether the clock goes to 0 to 1 or it is going from 1 to 0, it doesn't mind anything on that. If you give reset equal to 1, the next moment it makes my output to be 0. That's why we call this as asynchronous reset. So if I want to do that, I bring this positive reset or negative reset, whatever you wish, right? Active, inactive, like that. You can have positive or negative reset also. Bringing that in the sensitivity list means either this or this is true, then immediately it start entering inside. And if reset equal to 1, it makes my output to be 0. It doesn't wait for the next subsequent clock. That's the main part of it. All the other things are same. That's all. So a D flip-flop, you can have all this variant. So when you see a D flip-flop, you'll have multiple variant of that. Now we will try to see some of the variant. In fact, I have done a couple of things. Yeah, first let's take this code. Now, yes, can someone say what is this? What is
D
this
flip
code?
D flip flop
D flip-flop
synchronous.
with a
Synchron.
Synchronous, then
Active high.
active high reset. What do you mean by active high reset? If I give reset equal to 1, the output goes to 0. Active low, then if I give reset equal to 0, then alone it will go to 0. So again, so many places you could see active high, active low. Uh, you could see like a bubble in the reset, that is active low, right? So that's what you could see here, module D flip-flop, synchronous, active high reset. So I have mentioned D, Q, clock reset. Input is clock reset D. Output, I am declaring that as a reg. This is again more important because this is going to store this value. Even if it is a D flip-flop, the output need to be declared as a reg. That's more important, right? Okay. Always at passage of the clock. So it means that it is going to sync with the clock. Only at the passage of the clock it is going to take place. If reset equal to 1, then output goes to 0, else D equal to Qn. Now in this I can make too many variant. 1, in the same passage, you can make it as active low. Means, how could I make active low? Someone?
Negate clock.
No need. Active low. Active low.
Shift exchange if and else.
Come again.
Exchange if and else. Whatever is inside if you can put it inside else, and whatever is inside else you can put it into.
Simple. No, no. You need not to complicate that. If you keep reset equal to 1, then Q equal to 0. You simply put an alas symbol over here. Then what does this mean? If
It is not
alas RST, that is exclamatory RST equal to 1, then it is 0, which means the output will go 0 if you give reset equal to 0. That's active low. That's all. That's the only simple change you need to make. So straight away I have given RST. So this is an inversion of that. That's all. That's one variant. Again, you can have one more. Yes, something to be asked? Okay. Um, One more variant is, instead of having a passed, I too can have a negate, right? So actually a flip-flop is a passage latch with a negate latch combined together. You call that as a flip-flop. In fact, in the digital you would have studied, it's one master-slave flip-flop. Means one will be acting as a master and the other one will be acting as a slave. In fact, you can prove the two latches together. When you try to draw the timing diagram, you will understand that though one is capturing during the on period and other one capturing during the off period, the final output will be like the output which has been captured during the transition, right? That's how you build a D flip-flop. Okay, fine. Now let's try to simulate this. This is D flip-flop, synchronous active, high reset. Go to simulate, start simulation. D flip-flop. Active high, I believe. Active high reset. So let's take clock reset DQ, add to the waveform selected signal.
Sir, you have selected asynchronous, sir.
Is it? Oh, sorry. Then any one of that should make going to be 0. Let's try this also then. So force clock here, clock, then D you can give some value of 1, then reset. Let me initially give, this is active high, right? Asynchronous active high. So you can make it as initially 1 and then make it as 0, right? So let's try to see what's happening. So clock, you get it. So since the reset is 1, your output is 1. Now let me change the reset as 0. Immediately the output, whatever there in D should appear in Q. Yes. See, look at here. I make a reset. It doesn't wait for even clock. Of course, both are coinciding at the same time. If I am making my input, I mean reset 0, right? Then whatever there in D that is appearing in Q, let me make a reset to be 1. If I make reset to 1, the next moment output should go to 0. It need not wait for a clock. Yes. When I make reset to be 1, then my output goes to 0, right? Q goes to 0. Yes. So if I make 1, I am getting my output to be 0. Are you following this? So this becomes an asynchronous. One more, let me check with synchronous also. Yeah, this is passage of the clock, neckage of the reset. Oh, this is with neckage of the reset. Means if I give, that's what I was wondering a little bit. Neckage of the reset means whenever my reset goes from 0 to 1, then alone it will be entering inside, right? Passage of the reset means it will be sensitive towards reset moving from 0 to 1. This is neckage means 1 to 0, 1 to 0. So whenever you make a change from 1 to 0, now it is 1, you make it as a 0. Force 0. Yes. So whatever there in D has been passed on to the Q. Yes. Very similarly, if I am changing, you can even make this as a passage of the clock, passage of the reset also. So you can try with all possible options. But in order to avoid confusion, it's always better to have synchronous, right? Active low reset. That will be much more sufficient. Until unless you have some very specific need, you need not go and use all these possible combinations, because very frequently the thing which is being used is D flip-flop with synchronous high reset. Again, let me go ahead and see that is available. D flip-flop, that is synchronous active high reset. Okay, that's fine. Right. So I'm just adding up all this waveform, selected signal. Typically, you can follow the same procedure. All the other things are, you can try with all possible combinations. Twice, since I have added signal twice, I'm getting, so let me assign this for a clock. Okay, D, let me give force some 1 and reset again, let me force 1 for this. Then let me try to simulate it. Okay, these signals you can just remove it from clock. But still it's running. But that's okay. Let's stop running and then do that. Anyway, now the point is, you could see here, when I make reset equal to 1, the output goes to 0. Though my value is, D value is 1. Now let me make force this reset equal to 0. Now again, let me try. Now you look at the output Q, it is following D. Whatever available in D, that is being available in Q. Now, if at all, if you are making reset equal to 1, that will get reflected in the next clock cycle. Yeah. So I made reset equal to 1. That is getting reflected in the next clock cycle, coming clock cycle, because here I made 1. The next clock cycle, though here I made it, it doesn't take place. It takes place in the next clock cycle, Q equal to 0. That's all. So like this, you can go ahead and explore all possible combination of a D flip-flop, but mostly this synchronous reset with active high is being used at multiple places. All right. So you can use almost whenever you say D flip flop, you can just go ahead and define like this. Right. The next one, using D flip flop, as I said, you can build up many shifters, things like that, and you can also build counters also. Let's try to make one counter for it. I think the design, all those things you can refer in your textbook, standard textbook. For want of time, I am not going and discussing how to design. In fact, I kept 2 YouTube videos. If you are okay, you can even go through that counter. Apart from that, also I have kept 1 or 2 video lectures for VLSI stick diagram, things like that. In fact, I think it has crossed to 25,000 views. Maybe you can cross check that also. Long back, I have seen that. In fact, it was little bit noisy. It was a trial and error basis. Once, I think more than 2 years back, I have done that. 1 or 2 years back. It's available in the YouTube. You can just check it out. Right. So coming to counter, I have made one counter. Now let's see. Yeah, comparator also we have it. Counter mod 4. Let's see what is this counter mod 4. It's a very simple code. So where we need is module counter mod 4. So here I have made your input is nothing but your clock. So whenever you get a passage of the clock, immediately the count get increases, right? It's something like what you get from a sensor. Whenever if someone crosses that, then you get a pulse. For every risage of the pulse, you could see the count keep on incrementing. So that's how it has been made. Counter mod 4. So it's a 4-bit. It goes from 0 to 15, right? Clock clear. So if something want to be made, as far as the flip-flop which need to be used for counters need to necessarily have clear and preset, right? Or sometime reset, whatever. Preset is used for setting a value 0 or 1 in my output. This is mainly required with respect to counter, right? So I have already said, like it is very difficult to determine the output of a counter, not counter, D flip-flop, because most of the D flip-flop, when it is being chained up, it is acting like a memory. So you don't know what was my previous state, so it is very difficult to find out what is the next state. So they have 2 extra signals to make my output deliberately to 0 or to set a value to the output. That is one. That's called preset and clear. So clear I have kept here. Count out is my output. So input clock and clear. Output is reg 3 down to 0. Counter I have said 4-bit as my output. Always at passage of the clock or passage of the clear. When you give a clear signal, all the output count goes to 0. That's what we are doing here. Begin. If clear equal to 1, so this becomes count out 4-bit becomes 0, else count out will be count plus 1. That's a very simple code. Let's go and simulate that. Go to start simulation. Counter module 4, yes. So you can just select the input and output and pass it on to the waveform, selected signal. Okay. Gone. Yes. So in this now clock, I am forcing the clock. Give right. Clear. First you give 1 and then let's make that as 0. So now it's start counting. When once you make clear equal to 0, irrespective of the clock, it makes my output to be 0, right? Now let's make clear equal to 0. I don't want to have clear, so make this as 0 and start simulating it. Now you could see once I make it 0, for the first count it is 1, so it keeps on counting 2, 3, 4, 5, 6, it goes up to 15. Again it starts with 0, so this count keeps on going ahead, the binary counter, right? Similarly, you can have a ring counter. I believe you know what is a ring counter, Johnson counter, all those things you can even code it. We have already done that. So a ring counter is something like this. Just for a recollection, I'm just giving you. So if you have a 4-bit ring counter, A, B, C, D. So first, this first bit is 1, 0, 0. Then it will move on like this, and move on like this. It move on like this. Again, this will come to 1. For every clock cycle, it goes like this. If it is not the ring counter, you can just convert this ring counter to Johnson counter also. So first, if it is like this, second count, it comes like this. Third, it comes like this. 4, it comes like this. 5, it comes like this. Then again 1, like this. So instead of 0, you will have a subsequent 1 coming up. Now let's try whether that's working on. Again, I request you to refer your standard textbook for the counters. Counter design. Yeah, let's go with ring counter. Ring counter is something here what we have mentioned. Ring counter, clock, reset, D out. So D out is a 4-bit. So wherever you declare a temp variable, and that you need to declare that as a reg. Always at pass it or reset. This is again, this or can be, you can do that, or you can even put a comma. That's left to you. Okay. Begin if reset equal to 1, make all this temp to be 0, because at the last I'm going to assign this temp variable to my output. Else what I'm saying, temp out temp 0, that is 0th bit of temp. 0th bit of temp is this one, whatever value you give in, comma, temp 3 down to 0, 3 down to 1. So this last bit alone coming friend. Have you noticed this one? Say, let's assume that you have 4 bit, right? You have 4 bit. Now simply what we said is, you bring this and keep your MSB and this to be your LSB. Again, for the next clock cycle, bring this as your MSB, this as your LSB. That's why you get a shift. Can you see here? Temp equal to the last LSB comes as MSB and the remaining bit goes as your MSB. I mean LSBs. 3 down to 1 because 3 of temp of 0 came to be as your MSB. For every cycle, it keeps on rotating. That's a very simple code. Go here to simulate ring counter behavioral. Ring counter behavioral. Yes. Now we will select all these 3. Go to waveform. Oh, what is this? It's counter only, no? Ring counter only. Sorry. I'm just confused. Right. Give this clock. You give the clock. Reset. Let me force first 1 and make it to 0, and then we can make it to force 0. Now let's see. Now look at this case. First here the 1 is here, next it is moving on to the next place. So for every clock cycle, it is moving to the next right hand shift by 1 bit. Again coming to the first position, second position, third position, fourth position. Right? Can you see this? This is a simple ring counter. You can even make the Johnson counter as such. The only difference is you have a slight variation. Let me try to show that also. Go to simulate, start. Johnson counter, give it to OK. So again, I'm selecting a couple of things, add it to the waveform, selected signal. Right. So this is the Johnson counter which we are looking for. Let me give the clock. I think the first one is the clock. Yes, go ahead and force the clock. Then reset again. First, let me force 1 here, and then we can make it as 0. Let me force 0, and then yeah. Now you see how the pattern changes. Can you see here? The new one keep on adding it up. 3 1 4 1, again 1. First one becomes 0. Zeros 2 0 3 0 4 0, again 1 2 1 3 1 4 1. This is a simple Johnson counter. Yes, this pattern I think you would have seen in your textbook also. Yes, that's all. I think we have covered most of the combination and sequential circuits. Now, for completion's sake, you can also see the comparators. Let's take a break of some 5 minutes, and then we will start with the test bench, how to write a test bench, and FSM. Those two we will check it out. We will have a break for